Nice to be here and for the opportunity to talk here. So, is it on? Oh, okay. So Tauberian theorems are a natural umbrella term for dealing with any kind of divergent series and its rate of divergence. On the other hand, we also know that in CFT, a lot of high energy asymptotics are universal. So Tauberian theorems gives us theorems and techniques gives us a natural framework to analyze and extract these high energy asymptotic data in CFT. So today I'll mostly be focusing on 2D CFT, and so in 2D CFT it turns out that the asymptotic density of states or the asymptotic OP coefficients, these are controlled by very few parameters and they are universal. So our idea would be to apply these Tauberian techniques to rigorously derive those leading formulas and also probe some finer details of asymptotic behavior, which was otherwise not possible to do by doing naive analysis. So as you all know, like any other CFT, the 2D CFT consists of a bunch of operators. So we have an operator spectrum, then we have 3-point coefficients and also a central charge C. Like now this operator spectrum and 3-point coefficients cannot be arbitrary, they had to satisfy some consistency conditions. So as we all know, we implement crossing symmetry, which constrains the CFT data. So there is a huge bootstrap program on this. And also in 2D CFT we have one extra information, which is modular invariance, so which is some invariance of a torus partition function. So this also constrains the 2D CFT data. So in this talk we will only be using the modular invariance to say something about the asymptotic data. So pictorially, before that, so roughly this is the rough motivation. So if we can probe the finer details of asymptotic behavior of density of states, at least in the large C context we can say something about the black hole density of states. And also just from a pure 2D CFT perspective, this analysis is like quite universal, because given any CFT, I am giving you a formula or some bounds which is applicable to any CFT as long as it satisfies modular invariance. So we can probe the density of states, we can probe the various 3-point coefficients, the asymptotic behavior. We can also make the original Cardy analysis sensitive to spin, so we can probe the asymptote on this plane. And on plane things becomes much more interesting, because one can approach infinity along various curves. So they are really and the asymptotic results, basically the subleading terms are sensitive to this approach to infinity. So pictorially this looks like this. So I know something here, and the modular invariance relate this something to something on this corner where both of them large, and then the idea is to rigorously figure out the behavior of various physical quantities on this regime. Okay. So roughly this is the plan of the talk. So first I will go through the very basic things, the modular invariance, then I will do the naive Cardy analysis, which has been there for quite a long time, and then we will see there are some mathematical issues with the Cardy analysis. So in the next part we will use the Tauberian techniques to fix those things, and then we will also probe the finer details of the Cardy analysis. And then we will write down a spin sensitive Cardy formula which are sensitive to both H and H bar, and then if time permits, then I will also do the Cardy analysis for OP coefficients, and we'll comment about some issues with this when you do the same analysis with OP coefficients. Okay, good. So the modular invariance. So we all know that modular invariance deals with the partition function, torus partition function of 2D CFT. So what is a torus? Roughly torus. So torus is precisely, you consider a plane, and then you consider two vectors, and then identify the points on the planes which are separated by some linear combination of those vectors, and these identifications will give you a torus. So you have two cycles on the torus. Physically one cycle represents the thermal cycle, and the another cycle is the spatial cycle. So now the whole point is these two vectors are not any spatial. So you can do a transformation by a matrix such that this A, B, C, D, these are integers, and AD minus BC is 1. Then from one basis you can go to a different basis, and these two vectors will also represent the same torus. And on the other hand, I know the CFT is scale invariant. So, the partition function can only depend on the ratio of the two cycles. So, we define a parameter tau, which is called the modular parameter, which is basically the ratio of alpha 2 and alpha 1 viewed as a complex numbers. And this transformation induced this Mobius transformation on tau. Again, here a, b, c, d are integers and a d minus b c is 1. So, this is a SL2G transformation, and the physics input is the partition function of a torus partition function of a 2D CFT is modular invariant, that is z of tau is z of a tau plus b divided by c tau plus d. So, we will be using this information over and over again. So, that is the basic idea of modular invariance. So, now the naive Cardy analysis goes like this. It specifically uses this S modular transformation, which takes tau to minus 1 over tau, and if I write in terms of beta and L, the length of the thermal cycle and the length of the spatial circle, this implements basically a inversion or exchange of two cycles. So, beta over L becomes L over beta, and in particular this means if I take beta going to infinity limit on this side tau going to 0 basically. So, modular transformation relates the low temperature behavior with the high temperature behavior in CFT. So, if I know something about the low temperature behavior, if something is universal about the low temperature behavior of the partition function, then it is also universal in the high temperature sector. So, in the next case I will be writing down the partition function in terms of a Laplace transform of density of states. So, this is the well known canonical partition function, and there is a shift by C over 12 because CFT on a cylinder has a ground state energy of minus C over 12. So, from this slide we can see, roughly speaking, rho of E is inverse Laplace of Z of beta. So, we will keep that in mind, and then we will see that in low temperature, that beta going to infinity limit, the low energy dominates this partition function, and while on the high temperature limit, where is beta going to 0, the high energy dominates. So, if somehow I can figure out the behavior of the partition function in beta going to 0 limit, I can do some inverse Laplace naively speaking and figure out the behavior of the density of states. So, at this point our goal is to figure out this quantity, and that we can easily do using modular invariance. So, this is how we do it. So, in the beta going to infinite limit, the ground state contributes, and the ground state is controlled by a single parameter central charge. So, the behavior is like this. Then I do a modular transformation, and then I get the high temperature version, which is exponential 4 pi square over beta times C over 12. So, once I have the high temperature data, again I recall that rho of E is inverse Laplace of Z of beta. So, I take this expression and I do an inverse Laplace and I obtain a Bessel function, and then basically I know that this formula has to be valid in a energy going to infinity limit. So, I do an asymptotic expansion of Bessel function and I get the famous Cardy formula where it has an exponential growth. So, this is the most basic example of analytical modular bootstrap, where just by imposing modular invariance I am gaining something very universal in density of states. So, one can do further, one can make the analysis sensitive for very heavy Virasoro primaries. So, one write down a partition function which is sensitive, which only counts the Virasoro primaries, and for C greater than 1 it is possible because the characters are universal. So, one can multiply the partition function with the Dedekind eta and get some modular covariant function, and then do the same analysis on that, and then obtain that the number of Virasoro primaries also goes like Bessel function, which is also has exponential growth. So, this also shows that we need an infinite number of Virasoro primaries for modular invariance when C is greater than 1. And this is a very generic feature. Even we will see even in the Tauberian analysis, the results can be made sensitive to Virasoro primaries at the cost of slight complications, and one of the key ingredient is C is greater than 1. So, the characters are universal. So, whatever I will be saying later is applicable to analysis for all the operators and also applicable to analysis for Virasoro primaries with C greater than 1.
So to get the density of Virasoro primaries, you replace that e to the you replace I mean you weight your rho of E over the character of the primary.
Yeah, right, exactly.
Over the partition function.
Yeah, so basically it's a reduced, so z of beta times Dedekind eta becomes the reduced partition function for Virasoro primaries only.
Sort of like just like dividing out, right?
Yeah, exactly. For each Virasoro primary, there are a number of descendants, and all those descendants has a exactly. Yeah, exactly. And that's why I need C for C less than 1. There are null states, so I do not have a universal formula, so I cannot do this. Yeah, exactly. So this has been known for a pretty long time. So Cardy has this formula from 1986, and this formula is also known for a pretty long time. So here our job is to figure. So at this point, when I learned this technique, the first question that came into my mind, which is pretty natural, which is how one can approximate a bunch of Dirac delta function with a smooth Bessel function, because the actual density of states is bunch of Dirac delta has a support on the physical spectrum. So it's not as continuous, it's not a smooth function, in fact it's not even continuous. So the naive answer to this question, what I got long back is like the heavy states are closely packed, so we can assume a continuum. But the point is this is not really true, right, because I know the descendants are separated by 1 unit. And suppose we become ambitious and we ask questions like how closely are packed the states. So if you want to answer those questions, that how closely the states are packed asymptotically, we cannot ignore this fact. So the whole lesson here that we learn here is that if we are careful about this thing, then we can actually say something about the asymptotic gaps and at least put some upper bound on the asymptotic spectral gap of Virasoro primaries. So that's one thing. And the second important, and okay, before that, so roughly this is the answer for so we know that it's a bunch of Dirac delta function, but if we integrate out or smear it out over a small window like this or over a window like 0 to delta, then this function is a piecewise continuous function, and then I can approximate a piecewise continuous function by some smooth function. So it is mathematically much more precise to talk about f of delta, which is the 0 to delta integral, or this a delta comma delta, which is like the density of states integrated over a small window. And also note that this quantity is basically related to the microcanonical entropy in delta going to infinity limit. So
the whole point would be when this approximation is sort of valid, when you can approximate density of states by this continuum limit. So that analysis would suggest that maybe the separation between the states cannot be too large. This is roughly the idea.
Yeah, roughly the idea is like you so you put some, so you can show that there is some upper and lower bound on this quantity, and only when delta is above some threshold value the lower bound becomes positive, otherwise you will see what happens. So yeah.
So you say that this microcanonical entropy is a piecewise continuous function.
Yeah.
But let's say you have this window and you are moving it, and as you encounter a new operator,
Yeah.
this becomes now the part of the integral. So isn't there a jump? Isn't this a jumping function?
Oh yeah, right. It's a by okay. That's why it says piecewise continuous. So
okay.
it's
So
like
it's
piece.
not even, before you hit the next one.
Yeah, exactly. So
Sorry, it's not just the non-differentiability, but actually.
yeah, it's actually a jump. Yeah, exactly. Yeah. So that's one issue, and so whenever we will be dealing with Tauberian analysis, we will be mostly focusing on either this or this, and in fact in 2D we will be focusing on this quantity. But before going into that, let me point out another issue with the naive analysis. So in the naive analysis, what do? We do basically look at the partition function in the beta going to 0 limit, then there is a leading term and there is an error term coming from the other operators over the vacuum. Then we do a Laplace transform of the leading term, we get the asymptotic density of states, and then we assume that the error remains small under inverse Laplace transformation, which is not at all obvious. And one might say that there are a bunch of terms, I can do inverse Laplace term by term. For each term I will get some contribution which is suppressed compared to the asymptotic formula, but then there are infinite number of operators. So, I do not have any control whatsoever on this error in naive way of doing this thing. So,
this error term is the approximation that you are approximating a piecewise function with a continuous one.
no.
Ground state and first excited.
So, yeah, so this is the ground state and this is the first, second and all the operators in the partition function.
Low temperature.
Yeah.
This is the high temperature.
Height in the dual, yeah.
You do it in the low temperature,
Yeah.
ground state, first excited,
Yeah.
and then dualize.
Yeah, exactly.
So the fact that you're truncating to a finite number of terms is in the low temperature is your error.
Yeah, exactly.
So the fact that you ignored every other operator apart from identity, this is what you are calling error.
Yeah, exactly.
If you're naive and you just look at what the first term is,
Yeah,
you can get an estimate for the error.
yeah,
And then the question is that reliable? Right?
yeah, exactly. Yeah, precisely. Yeah.
From the perspective of states, you had discrete number of states and density of states was discrete.
Yeah.
And then you approximated it with a continuous function, which is the answer you are getting from the leading term.
Yeah, right.
And so this answer has some corrections because it has to be discrete.
Yeah.
So that has some corrections. And
Yeah.
that correction is related to this error.
No, so the point is we will show that the error gives you some under inverse Laplace gives you some correction to the asymptotic density of states, but that is not the error. That error is dominated over by another error which comes from smearing out the window. So
in this usual 4-point bootstrap,
yeah,
when one makes statement about the OP densities and whatnot for the heavy operators, in the large spin limit, one
Yeah.
can justify this type of approximation
Yeah.
where you ignore the
Yeah.
operators.
Yeah.
So only the leading twist.
yeah.
This kind of thing can be justified in the large spin limit.
Yeah.
So is there perhaps a limit in this H bar space, a line where the large spin line, where this is justified?
So the thing is like people, so here's the point. So sometimes people use inversion formula to justify that thing. So there is no inversion formula available in 2D CFT, so that's one point. And another point is, so Richkov and Xiao wrote a paper back in 2017 where in appendix A they talked about this leading twist thing, and I guess according to Richkov the issue is not really settled even in that scenario, like in the proper Tauberian way. And there the problem is it's become a two variable problem with z and z bar, and there is some issue with uniform limits and things like that.
But this picture of particles going
Yeah.
around each other very far away,
Yeah.
and then the spectrum being not very different from that of the 3D.
Yeah, and also there is another issue I must mention, that in higher D CFT you have a twist gap because it's a SL2R, but in the Virasoro it's not really guaranteed that whether you have a, because the bound is basically the unitarity bound is just h bar greater than. So if you want to do that kind of analysis, you need to assume that there is a twist gap in the Virasoro primaries and make the analysis sensitive for primaries, and then you can proceed and think of doing something.
Now, a free theory.
Oops, what happened? This is too bad. Yeah, say?
A free theory would be the theory. So going back to your
Yeah.
discretization.
Yeah.
A free theory is probably the place where it's most severe, right? Because let's say you take a free boson, 10 free bosons,
Yeah.
C is greater than 1, and you do your analysis. Here, your gaps will not actually be small.
Yeah, or monster, for example, even.
Or
Yeah.
just free bosons.
Yeah.
Okay. So there you could probably, independent of your detailed analysis that you do, you could probably just look at the exact answer
Yeah.
and see how well Cardy's formula.
Yeah, exactly. Yeah.
And presumably there are errors which you can
Yeah.
with the analysis.
Yeah.
You'll tell us about that.
Yeah, I will take the 2D Ising example and the monster example.
Okay. Monster.
And
What? One you might not see. Okay.
so yeah, so before moving ahead, I will briefly
Yeah. Sure.
before before moving ahead, I will tell you briefly about the okay, before going that, I guess I should tell you the immediate goal. So mostly our goals are following. So making the leading analysis of microcanonical entropy rigorous. So this was first pointed out in appendix C of our paper, and then later like Bauer and Sasha figured it out all, like doing the analysis very rigorous using some complex Tauberian theorems. And then they also figured out subleading corrections. So we have been able to improve their corrections by some amount, and in some cases we have found the optimal bounds and have proven the optimality. Then we also derived the optimal upper bound on asymptotic spectral gap of Virasoro primaries for central charge greater than 1. So this number has been conjectured in this paper by Bauer and Sasha. Then we actually prove it by using some function. And then also we can estimate this 0 to delta integral with some optimal error term. So this has been done in Bauer and Sasha's paper, and then we can generalize and develop further techniques of this Bauer and Sasha's paper to derive Cardy formula, which is sensitive to left and right movers separately. So here things becomes much more complicated because it's a plane, but still one can approach infinity along various curves, and for different curves you can prove Cardy like formula and probe bounds and things like that.
So one last general question.
Yeah.
In the general issue of approximating a discretum by a continuum goes beyond 2 dimensions.
Yeah.
For instance, in n equals 4 Yang-Mills theory,
Yeah.
you ask what are the errors in
Yeah.
estimating density of states, and your techniques, those general issues could also be addressed outside too. I mean, not unrelated to Cardy's formula.
Exactly. So wherever you have these asymptotic formulas and like this discreteness, this kind of techniques will help. So the only input that comes from the 2D CFT is the modular invariance, which tells you z beta going to 0 behavior. But if to start with, if you know z beta going to 0 behavior, then it's like nothing related to 2D CFT, like everything is very generic. Okay, something is happening to my computer. Yeah, somehow I feel like these computers are extra smart. Anyway, okay, so these are the immediate goals, and before now diving into the details, I will briefly tell you what the Tauberian things are. So broadly, as I said, Tauberian deals with divergent series and growth of partial sum. So this has a very long history. So the first theorem appeared in 1897 by Tauber, and then all these people have developed these things over. So there is a nice book by Korever on this history of Tauberian theorems. So roughly this deals with sums. So suppose I have a sequence AK, and if I do the partial sum with write down Sn, and suppose this is divergent, so as n goes to infinity, Sn goes to infinity. Now, to control this sum, I introduce an exponential factor and write down some kind of partition function, and suppose for beta greater than 0, this sum is convergent. Now, of course, as beta goes to 0, this boils down to this partial sum, and this of course has to diverge. So the Tauberian theorems basically is an umbrella term for this kind of theorems, where the input is the divergent behavior of z of beta as beta goes to 0, and then I can tell something about the growth of Sn provided some Tauberian condition is satisfied. In most of the cases, the Tauberian condition is nothing but this An is positive.
As I was asking earlier, so this the divergence can be not just not at beta equals 0 but earlier also, right?
Yeah, exactly.
And
So
in that case, the analysis near that will also give you similar.
yeah, exactly. So the 0 is nothing really, not really very special. Like
Take this hydron. recent example of interest where this positivity of AN is violated is when you try to analyze the n equals 4 index.
I see. So the point is this positivity. So later we figured out. So okay, this is kind of going ahead, but I should tell. So when you do the analysis for OP coefficients, for example, the heavy, light, heavy, they need not be positive everywhere. So, but there is a slightly cure. So the point is this positivity is not really a necessary requirement. So you can let it be negative, but not very much negative.
Probably not very fast.
Yeah, exactly. Right? Yeah, exactly.
So, and in the case of the n equals 4 index, apparently the thing does very fast oscillate, and many people, including myself, made wrong statements by doing that.
Yeah. So yeah, if it oscillates very rapidly, then it becomes very tricky, to conclude anything. But yeah. So the most basic example is the Hardy-Littlewood. So this is basically a generalization of Tauber's theorem, but yeah, so this is the most simplest example of, so where z of beta going to 0 is 1 over beta, and this tells you that the partial sum grows like capital N. And in our case the scenario is slightly different because the divergence is much severe, which is like exponential pi square c over 3 beta. So we cannot directly apply Hardy-Littlewood, but so here the point is most of these Tauberian techniques are, we not really like picking up any theorem from a book and applying it, because those theorems are not tailor made for CFTs. But what you can do, you can go into those things, learn a little bit of techniques, and then come up with your own proof. So that's what Bauer and Sasha did, and basically what we did is further generalize their techniques and come up with the 2D analysis for, when by 2D I mean H bar space. So yeah. So now the main analysis part. So as I said, we want to estimate this density of states integrated over a small window. So I write this down as a rho of delta prime with a bump function. So this blue is the bump function here. And now the idea is that we want to approximate this bump function from above and below, this black and the blue, black and the red line, so that this is very smooth functions and they are band limited. That means the Fourier transform of this black and the red functions have bounded support. And we will see that it is important to have bounded support. For example, like on the contrary, if you look at this bump function, the bump function has a Fourier transform which is not at all has bounded support. So that's why we needed to approximate this with a black and the red line. So we cannot just work with the theta function here or this top hat function here. So once I do this, I write down an inequality like this, where phi my
This black thing is totally positive?
yeah, because it has to be, because it's above the bump function, and the bump function is 0 outside the window. So this black thing is always positive, and within the bump it has to be greater than 1. And on the other hand, the red thing is within the bump it has to be less than 1, and outside the bump it has to be negative everywhere.
And the integration of these two functions with respect to the density is what is going to bound this A
Yeah,
from above to
yeah.
and that's where positivity for example.
Yeah. At some point you have to multiply with rho of delta inequality, and that's where in the next slide you will see it.
Both of these functions integrate to 1.
Oh no, it's
Neither.
yeah, neither. Yeah.
It's just inequal.
Yeah. So yeah. So we start with this inequality, which is a basic one. Now you multiply this inequality with these factors.
So this inequality is stronger than what you need, right? The pointwise bound. I mean, the indicator function need not be inside the two functions for all values, right? Or does it need to be?
Wait, say that again. I didn't quite get you.
This step function
Yeah.
need to be between the red and the black curve for all points.
Yeah, that's what I am assuming. Yeah.
If it wasn't, suppose you had a state that
Yeah. Yeah, so I have this inequality, and then I multiply with these factors. So if you look carefully, then if delta prime is within the window, then this factor is, the exponent is negative, and this factor is less than 1. So, I can multiply with this and be safe. In the same way, if delta prime is within the window, then this factor is bigger than 1. So, I can multiply with it and be safe, and you will see why I introduce these factors. So, now you can multiply with rho delta everywhere and integrate from 0 to infinity. So, the middle one gives you the one you want to estimate, and here this exponential beta delta minus delta goes out, but this e power beta delta prime goes in, and here also e power beta delta prime goes in here, right.
Wait, we didn't understand this factor.
Oh, I can go into the board. So, the point is this
Delta prime will be the integration variable.
yeah
Delta
right
is just
yeah. So, delta is some
delta something.
yeah. So, the point okay, I guess so the window is like this. This is your delta, this is your delta minus delta plus delta, delta minus delta. At the end of the day you are doing this. Now, this factor here, so when delta prime is inside the window, this factor is less than 1, right.
Yes.
So, that means
Sorry, yeah, less than 1 this factor.
yeah. So, that means this number is less than this number, less than this number. In the same way, when it is inside the window, then this number is greater than 1. So, that means this is less than this is less than this. So, that means this inequality is satisfied when it is inside the window, and outside the window it is trivial because it is always negative and it is always positive, because outside the window phi minus is negative. So, it is always negative, and phi plus is always positive, this one is always positive.
And the actual thing is 0.
Yeah, exactly. And the reason we need to introduce this factor, we want to have the exponential minus beta delta prime inside the integral. So, that is the key insight. So, now we have this thing, and now if we look at this quantity, the integrand, in the Fourier space it becomes a convolution of the partition function and the Fourier transform of phi minus. So, that is the key insight. So, and you have this factor. So, basically you write down schematically in this form. There are factors of e power beta delta here which I omitted, but those are like details. Roughly you have this z of beta plus it convoluted with this phi minus t, which is the Fourier transform. Then you have number of states in the window, and here you have the other quantity. Is it clear? Okay.
Fourier transformation dimension?
Yeah. So, basically phi plus minus delta is integral dt e power I delta t phi plus minus t hat minus infinity to plus infinity. So, and this quantity what shifts the beta from beta plus it.
There is some exponential factor.
Yeah. So, there is a exponential beta delta factor and also like c over 12 factor which I omitted here, but yeah, you should be careful about all those terms when doing the analysis. Yeah, right. So, and specifically like when you are doing the large C analysis, you have to be very careful about keeping all the C terms because those will be crucial, but yeah. So, at this point, but now, so from the naive Cardy analysis we have this intuition that we have to go to the dual channel, because in the dual channel the vacuum contributes. So, the next nice thing to do is to do a modular transformation, and this making this z of beta plus it is z of 4 pi square over beta plus it, because I know in the beta going to 0 limit this is dominated by light states. So, at this point I have to figure out these convolutions and approximate the state number of states in that window. So, to do that I separate this piece out into two parts, one is the light part and one is the heavy part. So, the light part is the one where the states has dimension less than c over 12, and the heavy part are the states where delta is greater than c over 12. And the idea is the light part, because c is finite in this case, the light part has finite number of states. So, I can do this integral term by term and it will produce a Cardy behavior, and then somehow I have to show that heavy sector is completely suppressed as a whole. because I cannot do term by term for the heavy sector. And that can be done using the fact that this functions has a boundedly supported Fourier transform. So specifically, like if we do the full analysis, we will see that for the suppression of the heavy sector, we will need that the support of the Fourier of phi plus minus is less than twice pi. Oh, so it means that if you evaluate this phi plus minus t, then like it only has values from minus 2 pi to plus 2 pi. Outside that window, it is 0.
You choose that.
Yeah. I choose those kind. Yeah.
Plus minus 3.
Yeah. And
Sorry, but this has to be from 0 to 2 pi or anywhere in the 2 pi window.
so in principle, like so
Minus 2 pi.
yeah, minus 2 pi to plus 2 pi basically.
Should have too large.
No, but can this not be shifted in the frequency?
Yeah, so ideally if you use the fact that spin is an integer and things like that, then it can be shifted, but the best estimation you will get from using minus 2 pi to plus 2 pi. So
I don't quite see how these packets, if that's always possible with that support, produce such packets.
oh yeah, you can write down functions, yeah.
And delta doesn't enter this at all. Little delta.
So little delta will appear in the leading behavior.
No, but what I mean is that irrespective of what little delta is, you can always choose 2 pi. It's not 2 pi by delta.
Oh yeah, right, yeah, right.
But as Shiva was saying, if the delta is very small, you would need a larger support.
Yeah, then if the larger support becomes greater than twice pi, then you cannot use that function, and that means you cannot squeeze your function.
Some condition on delta.
Yeah, that's your bound basically.
And would you be showing why that heavy sector is suppressed if you can find such a thing with that support?
Okay, it would be slightly detour, but if I can go if you want. I don't know.
It would be nice if you put out.
Oh yeah, so roughly it is something like this. So you have this thing here, then this thing is nothing but this plus IT delta minus C over 12. Now basically if you take a mod of this thing, then this is less than e power 4 pi square beta this thing, right? Now the crucial point is if delta is greater than C over 12, all these exponents are like these exponents are negative, and now you have a t square here. Now if you put t equals lambda, where lambda is the support, that's the maximum possible value it can attain, right? So that means this thing is bounded by e power minus 4 pi square over beta square plus lambda square delta minus C over 12.
Delta is the maximum value that the support can have, where pi, delta is pi. Lambda is pi.
Yeah. So the point is, at this point you still do not know what the value of lambda is. So you need to estimate this quantity, and then you use the result of H case, which tells you that this thing is same as e power basically the dual temperature 4 pi square over 4 pi square beta square plus lambda square times C over 12. And you have to see it in the beta going to 0 limit, so this will give you, this goes away, so this will give you lambda square over beta C over 12, and this thing has to be suppressed in the beta going to 0 limit compared to the Cardy formula, and this precisely gives you some bound on lambda which is twice pi. And here it was crucial that delta is greater than C over 12, because only then you can replace this t square with lambda square. So that's why this light and the heavy sector was important. And this becomes really complicated when you want to do the analysis for H bar. Then you have to cut the plane in various ways and estimate different parts in different ways, and things becomes a much more mess. But still you can do it.
What about the light states you mentioned?
so the light state is in the other part, and that part is evaluated separately, and that will give you the leading answer. And the heavy states are estimated this way.
It's completely different analysis.
Yeah, so you separate out two pieces. The light pieces give you the leading part, and the heavy piece you estimate this way, and on putting this condition you show that these pieces are suppressed compared to the leading part. Oof, I am sorry about this.
Can I ask this again?
Yeah.
Start from the modular transformation perspective.
Yeah.
You have taken the contribution only from identity operator. So all errors is coming from the other operators.
Yeah.
And from the perspective of states, it's you have got a continuous function. You are supposed to get.
What do you mean by from perspective of states?
So from the perspective of spectrums, we have discrete spectrums.
Yeah, yeah.
We have states.
Yeah.
And the density of function is supposed to be some very jaggedy function.
Yeah.
But we have approximated it with a continuous function, which is the contribution coming from the leading term,
Yeah.
which is the identity operator.
Yeah.
So the fact that I have forgotten the function has jaggedness is the fact that I have forgotten contribution of other operators.
Yeah, in a way that, yeah. Then?
Okay. So now you said that it is always possible to choose phi plus and phi minus to satisfy this condition that it is within.
Yeah.
So in a way it is saying that I can always suppress this contribution because these functions exist.
Yeah.
We can always suppress the correction terms as long as this condition is maintained.
Yeah.
So it says that you know the states in high energy sector are not too widely spread. This is
State.
in the high energy sector you have various states.
Yeah.
And the distance between these states are not too high.
Yeah, it has to be that way on yeah, right, that's true. But then you have to write down a proper function which relates the delta with this lambda, as Abhijit was pointing out.
Yeah. Sorry, after you finish.
No, this is the logic that because this function exists, therefore there is this.
So the point is the point is that just the existence of function doesn't guarantee you anything. You have to write down a function and then relate this lambda with the delta.
Right. I agree there is an analysis. I replying that, but I'm just trying to understand.
Yeah. So the point is the function exists tells you that there is some bound, but then it doesn't tell you whether the bound is exponential 100 or 1 or exponentially minus. Yeah.
So just going back to this phi plus minus.
Yeah.
The question of whether if its Fourier support is less than 2 delta.
Yeah.
The question of whether that thing. Sorry.
Yeah.
If its Fourier transform support is less than 2 pi, the question of whether it can satisfy the properties you want is a purely kinematic question.
Yeah, exactly. Nothing to do with CFT.
So there is some bound on little delta for which this is true.
Yeah.
And you can tell us that's some pi or something.
Yeah, exactly. Yeah, and that's the, exactly. In fact, it's like little delta is half. So the window is 1.
Okay.
Yeah. Okay, so we need this condition. And then basically, so the light sector gives you this inequality, which is the number of states here. Then you have this Cardy, rho 0 delta is the Cardy formula. And you see there are two numbers appearing here, C minus and C plus. These are basically integral over those phi plus and phi minus over the whole window. The one you were speculating it to be 1 initially, but it is of course not 1. So C plus is greater than 1 and C minus is less than 1. So at this point all it boils down to how much you can push down the C plus and how much you can push up the C minus to get the optimal thing. So that's one perspective of this analysis. And most of the results follows from like you choose different functions, you gain some intuition, you make it better.
So you're saying if you find such a function,
Yeah.
you can find C plus and C minus.
Yeah.
Which is that.
Yeah.
And then this bound holds, and you want to push up C minus, push down C plus.
Yeah, by choosing different functions.
And the larger you make delta, the better you'll be able to squeeze these two numbers.
Yeah, in principle, yeah. So the point is if I make delta to be very small, then C minus becomes negative and then it's meaningless. Like it's trivial, not meaningless, yeah. So there is a threshold value of delta for which C minus is positive and that's your bound.
As you smear over larger and larger distances, you can get a more and more accurate
Yeah,
assessment of this.
yeah, exactly. So
Uncertainty principle.
yeah, basically it's a band limited function. So it's exactly, it's uncertainty principle in some way, right? Yeah. So at this point, this problem becomes a purely mathematical problem. Like you choose functions and play with it. Yeah. So and also once you have the number of states within that window, so you can figure out the entropy, which is like log of that thing. So this is the leading piece. This is the piece that depends on the window. There is a log delta, and then there is a order 1 correction. So Bauer and Sasha showed that this order 1 correction is bounded by S minus and S plus, and this S minus and S plus is precisely related to C minus and C plus, with some like log of C minus and log of C plus is S minus and S plus.
And as you are saying, for delta large, S plus and S minus coincide.
In principle, it should coincide, but yeah, it's hard to show like that thing happens.
But what is the meaning of this thing there, the log which increases with delta?
Oh, so there is a piece.
Expected if delta was large, then Cardy result would be or that's the high energy state contribution.
Yeah. So the point is if let me understand. So this is a log delta piece. So if delta is very large, then these. So the point is you cannot take that to be very large because.
Then you're not getting the entropy at that energy.
Yeah.
You're getting the entropy around that energy. So there's some error.
Yeah. So delta is to be understood to be a fixed order 1 number. So and capital delta is very big. A little delta is a fixed order 1 number. So you cannot let it very big, and then that would be a problem.
Yeah, but just continuing on that, I would have expected from that point of view to see something like the Taylor expansion of S delta up here. But maybe this is because you're keeping S delta very small. Sorry, let me just say that again. So suppose the Cardy formula had been exact.
Yeah.
Just C capital delta by 3 had been exact. But you have a band.
Yeah.
Then you would get an error.
Yeah.
Because you're not probing just in that.
Yeah.
area.
Yeah.
And that error should have shown up somewhere. That doesn't look like that log. This log is not. I think it's not what I.
Yeah. So the log is coming from. So the point is the log is coming. The log is coming from the factor. So basically, you estimate this quantity, 1/2 delta, to be very precise. And this quantity and this twice delta is going up on the other side and gives you this log 2 delta. So it's.
Oh, that's exactly what I was thinking of. But that gives you a log, huh?
Yeah, because if you take the, so this is basically C minus rho delta, and C plus rho delta, rho 0, and then if you take a multiply with twice delta on both sides and take log, that gives you log of delta.
Oh, because you have a log in the first place.
Yeah.
Okay. No, so this is exactly that.
Yeah.
Just that. Not taking
Yeah.
the central value to
Yeah.
sphere.
Yeah. So this is the inequality, and because there is a 1/4 here. It's just the way of. So yeah, I don't know like why I wrote it this way, but yeah. So
Because it's one dimensional.
yeah, exactly. Yeah, precisely. Like if you do it on h bar, then it's delta bar. Yeah, exactly. So now. So basically, as I said, Bauer and Sasha put some bound, and their bound was tightest among a large class of function, but then it was not optimal. But then you can go away from this class of functions, and so basically we showed that it is possible to improve their bound for delta greater than delta t.
Sorry, could you show the last transparency? I just want to internalize that.
Oh.
So this is just the
So the first part is the definition, and the second part is the result.
Is the result for what? I didn't understand. For plus or minus or what?
Oh, no.
This comes only in that error term. That is fixed.
So this,
Fixed.
yeah, the first two is fixed, and the third one is bounded by
So
S.
the first two is just Cardy.
Yeah, exactly.
The second one is
Is
the
Cardy.
Yeah.
Okay, and that thing is the error. So that you're gonna tell us about.
That is basically bounded by two functions which can we estimate. Yeah.
So if I put the Cardy density there and do this integral, I will get the second term exactly.
Yeah, precisely, yeah. With this, yeah, right. And yeah, then basically Bauer and Sasha put some bounds, then we improved the bound for some delta greater than delta t by using different functions. And for a very specific case, for the lower bound we can show that we can find out the optimal value of S minus, that you cannot do better than that for that particular value of delta. I will show you later.
So on physical grounds, one would be interested in that value of delta where it's positive, where S minus is positive.
Yeah, right. So when I am when I am writing this inequality, I am assuming that S minus is like C minus is positive, so you can take log. So
No, I mean, if you want to estimate the minimum interval
Yeah.
where at least one state must exist.
oh yeah, so that's
That's like keeping on increasing delta, and
Yeah.
at some delta, the S minus will turn positive.
yeah, exactly. Yeah, right. So there are two different problems. One problem is, given the fact that C minus and C plus is positive, how much you can push it up and how much you can push it down. And then the next another question is like what would be the optimal value of delta so that C minus becomes positive. Yeah. And we also did a systematic study on how tight you can make the bound using the band limited functions. So this work has been done with a friend from electrical engineering department. So this guy is pretty good at doing the systematic study of how tight you can make the bound. So yeah, this part is credit is due to him, like so. And he is the school friend of Shubham. So yeah, anyway. So these are the results. So you can see this, I guess. So anyway, this is the orange line. So this orange line is due to Bauer and Sasha, and then we showed that for delta greater than this threshold value, I can improve this. And so this is the upper bound. So we have pushed the upper bound, and we also can do some numerics and show that all these regions are not real. Wait, I guess. Sorry, I told it other way around. So the blue line is the Bauer's line, and this orange line is ours line. Yeah, right. So you are pushing it down because this is upper bound, and then we showed that all this shaded region is not allowed with using the band limited function. So the optimal function has to lie somewhere in between.
Wait, so this the left on the axis, this 2 is just a number. It's log of number of states.
Oh, this C plus. So this C plus is this thing.
C plus. Sorry, the C plus entered in your error form. No, that S plus entered. C plus is different, right?
Yeah, C plus is exponential S plus basically.
C plus is exponential.
Because log is related. Yeah.
So, so exponential of C plus is the error in your entropy.
Yeah, log C plus is the
error number of error number of states.
Yeah, right.
So that's like if I see 2, that's like e to the power 2.
L-
Wait, sorry. Plus.
So this C plus is
C plus is just the number of states.
yeah.
Okay, so 2, you're making an error of 2 states.
It's not really 2 states because it's a multiplicative thing.
Which row not? Yeah, can you show that formula again?
Oh yeah, I guess I can write it down here. That would be easier because where.
Fractional.
So the formula is this: C minus rho 0 delta prime 1 over 2 delta, delta minus delta, delta plus delta, rho of delta prime, d delta prime, C plus rho 0 of delta. And this is true in the limit delta going to infinity.
And your S plus, the error in your
S plus is basically log of C plus. Basically you are taking log of the whole thing.
It's still quite an error, right?
Yeah, like
quite an error in states, but not
not in entropy. Yeah, exactly, because you take the log and it becomes like additive. Yeah.
And that is the dotted line, the one below, is that C minus?
Oh no. So the point is, so first of all you can do an analytical study on how tight you can make the bound. So these green lines are that, and then you can do a numerical analysis and show that whatever you do, you cannot do better than this line. Yeah. So this graph is all about pushing down.
No, but you're saying shaded region is not allowed this.
Yeah, so that means you cannot push this line down below this line.
So how did you get the shaded region in the first place?
Oh, so the point is, you know that your function has to satisfy some property, right? Now you can ask yourself that what is the best possible I can do theoretically given those constraints, and pose it as a mathematical questions, and that gives you this bound. So this is a bound on bound. So that's why I said this is a lower bound on upper bound.
So the top is what has been achieved.
Yeah.
The bottom is the limit. You cannot go below.
Yeah.
Something saturates it.
I'm
Inequality.
I'm not
Something
sure
would go
whether.
wrong if you went below.
Yeah.
No, something saturates that line, like some.
No.
Oh no.
It's a bound. It's impossible to go below that.
Yeah.
It may not be possible to reach.
Yeah, exactly. Yeah, and that's why this engineering friend came here, because came into play, because these guys are very good. Yeah, here there is no optimality statement. For C minus I do have an optimality statement, but for a particular value of little delta. So next we go to C minus.
Wait, so far you've used nothing about the CFT at all?
Oh, in this.
I think the key thing was that thing that you quickly did that.
Yeah, basically estimation of the heavy part and the modular invariance. That's the only two physics inputs.
No, but what have you?
So
What have you used that depends on the details of the CFT?
nothing. Just the unit, just the positivity of rho of delta and modular
So
invariance.
this is true for every CFT.
Yeah, exactly. So that's I guess that's the strength of Tauberian, this kind of techniques, that it's a very generic one.
But as Indranil was saying at the beginning of the talk, as you take more and more light states into account
Yeah,
in your Cardy formula,
yeah.
you should be able to use that to understand, the details of the spacing of particular CFTs.
Yeah, right. So for a particular CFT, you have to put in some extra informations.
So the light stuff still can be accounted for, right?
Light
That's
stuff
not being accounted for here because that's an exponential error.
Yeah, exactly. And
Much stronger.
yeah, so
the
this.
stuff coming from the heavy states which are being bounded is much stronger.
Right?
Yeah, so the point is the error coming from this C plus C minus, this thing, the error dominates.
Exponential.
Yeah, so the error dominates the error of that other states.
No, I agree. But if you were to sum all the light states,
Yeah,
you would get the full exact answer, right?
yeah, right.
You sum all the light states, then do the modular transformation.
Yeah,
You would get the full exact answer. So,
With some error having to do with the heavy states again.
but if you were to sum all states,
Yeah, all states.
you get the full exact answer.
Yeah.
So if you start doing more and more summations, you're
Yeah.
getting more information somehow.
right.
And somehow there should be something about that tells you more about the theory.
Yeah, so I can tell you
Something very universal.
tell you an example. So for example, if you take holomorphic CFTs,
Yeah.
then there is a Rademacher formula, which actually gives you that kind of thing, an exact convergent expression for density of
Few
state.
states give a lot of it.
Yeah, exactly. But it's not very clear how to do the Rademacher for generic CFTs, because you do not have the luxury of holomorphicity and things like that. But
Yeah, but just, I'm sorry to keep on, but just let me say once again, in a free theory,
Yeah.
you expect big spacings.
yeah.
In an interacting theory, you expect tiny spacings.
Yeah.
It would be nice somehow to collect some of that.
Yeah, exactly. Yeah, I completely agree. Yeah.
Okay.
Yeah.
Your analysis completely blind to all that.
Yeah. My analysis is like very generic, and I do not have put in that extra information, and it's not even clear how to put in that extra information into
Or
the.
what about the theory you need to put in?
Yeah.
That would be very tricky.
Exactly. For example, I guess a naive guess would be to assume twist gap in the Virasoro primaries or something like that, to see that.
Yeah, it would be nice if something about the low energy spectrum
Yeah.
controlled something about this spacing.
Yeah.
So, isn't this the statement that you think you break the spectrum apart into states with delta less than C over 12 and greater than C over 12, and in this first set, if you pick only the identity, okay,
Yeah.
and estimation of the heavy states,
Yeah.
then you get what you have.
Yeah.
Now what you can do is add the other light states,
Yeah.
and then your formula is going to get corrected, but it's a small correction, a very small correction. Right?
Yeah, and then the problem is then the heavy, so the heavy part is also like this, right? So this is comparable to the leading piece. So there also you have to like do some modification.
So what will change? I think in your formula, which the final formula where you
Yeah.
had microcanonical entropy as
Yeah.
being the Cardy result
Yeah.
plus S plus S, S
Yeah,
delta.
yeah,
There, the first two terms, which are fixed terms,
Yeah.
they will change, right? According to K.
yeah, they will change, right?
But that S plus S delta analysis will not change.
Yeah, right, but I worry that the point is that this S plus and S minus, this is like order 1 correction, and if you include the other light states, this will give you exponentially suppressed corrections. So there will be problem in like self consistency, because if you include those exponentially suppressed corrections, then you should have some control over this order 1.
S plus S minus.
Yeah.
further correct.
Yeah.
But Shiraz, you're saying somehow there is a source of order 1 errors also having to do with the
Yeah, I think that
light states.
if you take just one light state, as you say, it's exponentially suppressed. But somehow I feel that there should be some information in the light spectrum that tells you more.
Yeah. I like that's the.
Where it gets.
Maybe in the large sea or somewhere where you get many light
See,
states.
as you approach the place where it becomes almost halogen light or something. I'm not sure exactly where. But
Yeah, that's a very interesting question, like how to put in the extra information to say like see something, but yeah, it's not really clear at this point.
I mean, let me ask. Suppose we take. I'm really sorry, but
No, it's fine.
suppose we took a theory which had, as you were saying, a large twist gap. A theory that's governed by gravity.
Yeah.
Then we expect the theory to be governed by black holes.
Yeah,
at a-
right.
Where we expect the density
Yeah,
of space to be
exponentially.
very small.
Yeah, exactly. Yeah.
So these two things should be somehow related.
Yeah, exactly.
This large gap here,
Yeah.
very small.
But he is actually assuming large gap in some sense because
No.
he's not taking any light states.
No, but it would be fine if his gap was 1. But I mean, if the gap is of order C, for instance.
Yeah. So somehow, like if you want to do better, you have to exclude all this.
Sorry, your light states are from 0 to C by 12, right?
Yeah, right.
So you assume, let's say, which is already a tacit assumption, where you assume that there is no states, then only identity operator is there, and then only
Not really. You can assume that there are states. You do inverse Laplace of each one of them, but then at the end of the analysis, you will throw them out because like your order, there is a order 1 error.
Without stating, isn't it what you did?
Yeah.
You didn't assume any other contributions of the light states.
Yeah, right.
So how?
No, but he's just doing this. But we know independently that in a theory which is like gravity, there are two things that go together.
The gap and the fine.
Gap in the
Yeah.
in the light states and the black holes dominating, which means very finely spaced spectrum. Right?
Yeah.
This may be a more universal thing.
Yeah, right.
How to get to that?
I have no clue.
Maybe in the large sea.
Yeah, so the point is, I can tell you one more thing. So this is lambda less than 2 pi, right? So if you can make this number exponentially bigger, that would translate to an exponentially smaller window.
Yes.
So somehow in those kind of theories, we will have a very better estimate of a heavy things, which will make this lambda, which will allow you to take lambda to be very big. But then it is not clear what extra information should I put in so that I can do a better estimation of the heavy part and allow this lambda.
Large sea, no? Large sea.
So that's it can't be enough.
Yeah, for example, you can.
Fold.
No, but the gap is, assuming the gap, assuming the light state is only 1, let's say, right? State below C1.
Hello. Hi.
Hi.
I had a question. This is kind of related to the things that you guys are discussing. So this is about, throwing away these other light states.
Yeah.
So I understand that they're exponentially suppressed and you're kind of, trying to estimate already order 1 errors.
Yeah.
But is there a statement that if you kind of keep those exponentially suppressed states,
Yeah.
there's some, like corrections over those exponentially suppressed terms,
Okay.
which are kind of similar.
Yeah.
I was thinking of something like, like if you think of these various contributions as some kind of different saddle points contributing, okay? Is there some universality to the, like the fluctuations about each saddle point?
Right.
Like something like what resurgence people talk about and so on and so forth.
I
Is there
see.
something like that in your analysis?
So you are saying that the other operators, like the contribution from the other light operators, should come as some different saddles or something like that?
Yeah, I'm not very like sharp about that statement. But let's say we vaguely think about if you put the light operators and do Modular transformations,
Yeah.
you get some further and further exponentially suppressed contributions.
Yeah, right.
And, but I'm just asking, I'm just trying to see whether something can be said about them rather than just throwing all of them out. Though they are kind of suppressed compared to the errors that you're estimating.
So one thing I believe, that suppose you know the spectrum exactly, so you do not need to smear out, and then it might be possible to get rid of this order 1 error, and then it might be possible to like do better. For example, that this happens in the holomorphic CFTs where you have a Rademacher sum, because you precisely know the spectrum it's at integer points, and then you can write down a convergent sum which takes care of all the light operators, contribution from all the light operators. So at the least you have to know the spectrum, I guess, because some of the errors in C plus and C minus are coming from the fact you have to smear it out over a window. So if you can get rid of that thing, then maybe you can do better. So that's the intuition I have, but it's not clear like how to do Rademacher like things for arbitrary CFTs. But yeah, it's a like I don't know, like it's a good thing to think about.
Okay.
Okay. Should I proceed?
So when you say light states, the contribution because of the light states exponentially suppressed is exponentially in what?
In basically the gap. So it's like the is delta minus C over 12, and then it will be like further.
Yeah, but there could be cases where it's not a large gap.
Oh yeah,
Maybe that's where the non-universality
yeah,
will be apparent.
yeah.
Sorry, I'm sorry, one last question. As little delta goes to 0, what happens to C plus?
Oh, little delta goes to 0. It blows up, as far as I remember. Like
Yes, it blows up, and how? And is there a functional form for that blow?
I guess it's. Okay, I don't remember. It's like sine hyperbolic or something like that. Some function. Yeah, like it very steep.
Exponentially.
Yeah, yeah. Yeah, I can tell you the exact function later. Like, yeah. Okay, now comes.
Sorry, I was
Okay.
just thinking that it should
Yeah.
be, that if little delta goes to smaller, that it should blow up at a finite value of delta. Because we know that there are free theories where the spacing is integer spaced.
Yeah,
So if little delta, if your band, oh no, but now you've got this wiggly thing. It's not
Yeah.
the theta function.
yeah, yeah.
Okay. Had you done the theta function, you would get infinite error.
Yeah, so the problem with theta function is
between these two states.
so naively you can think I could have done the whole analysis with the theta function, but the problem is the Fourier transform of the theta function is not bounded, so this condition wouldn't be satisfied.
I'll just say, you're estimating how many states you have. Now let's say you've got a free theory, so all your states are integer values. So if your band was within, you contain that integer, you get the entry. But if your band was in between the two integers, you get 0.
Yeah,
So your error would be huge.
yeah, yeah,
But because you're not doing this theta function,
yeah, yeah,
it's not such a huge error.
yeah.
The error will only be
It's
huge.
a huge multiplicative error.
Yeah,
But that's some C minus or C plus.
would go to infinity or 0.
That's the C minus, right, becoming C to state.
C minus becoming 0.
Yeah.
Oh.
Okay, now comes the lower bound. For the lower bound, again the blue line is what they obtained, and then we improved a little bit.
No, but even the upper bound would go to infinity because you're weighting your, let's say you have some little range, you'd weight the states by the width of that range, and then if your width enclosed the integer, even though when the width is 0 you should
Yeah.
get no states, you get a huge number.
Yeah,
But that's some delta equals 0 statement.
Yeah, that's some delta equals 0. So that predicts that from the theta function, the thing should blow up like 1 by delta.
okay, I see.
Either Q is also finite delta issues.
Yeah, I'm saying as delta goes. Right. No, okay. Not for C plus. For C minus it's a finite delta issue. For C plus it sounds like a prediction. It goes like 1 by delta.
Yeah.
I'd like to say something. So this is related to something that Loga said.
Yeah.
My understanding is that, quite primitive, but then my understanding is that what your Tauberian theorems can do is they can determine subleading corrections to leading growth of
Yeah.
like a series.
Yeah.
Right? So now if I take this series to be an asymptotic series,
Yeah.
this is generic for like any kind of perturbation.
Yeah. Yeah.
Then the resurgence community, what they understand quite well is that the leading divergent behavior of this function will determine the action of the corresponding saddle.
Okay.
This is something that they know how to do well. You can take that one step further and say, what about subleading corrections to leading growth?
Okay.
And the understanding there is that, I think is the understanding that if you look at subleading corrections in let's say large n, right, then what that's going to do is that's going to determine perturbative behavior about that
Saddle.
next saddle, the other saddle.
Okay.
you're twisting. So my guess would be that like these sorts of theorems might be useful in sort of simple quantum mechanics problems. where you
Yeah.
have to determine
Yeah, I can possibly imagine that. That would be useful. Yeah. Yeah, I do agree. Yeah. Okay, so next comes the lower bound. For the lower bound, again, we improve this a little bit for some threshold value, and then all this region is not allowed.
For Hagedorn growth also this kind of analysis be done.
Yeah. Like exact details might be different, but naively. So one feature is very clear, very apparent in all the Tauberian analysis. Like you always approximate some indicator function or bump function like above and below, and then do the analysis, put some upper and lower bound which has similar growth. So the things that sits in between has a growth. So that feature is similar everywhere.
It's because you're cutting off this lower thing at an edge. Once you cut off the low spectral, it doesn't matter.
Well, I mean, this is coming from estimating the heavy states. This 2 pi.
Yeah.
That is where it came from, right? That you wanted to support, which was 2 pi. And then that came from the
Yeah.
estimation of the high energy states.
Yeah, estimation from the high energy.
At very high energies, it's never accurate. That violates the assumptions of a
Not in CFT, in general, I was just talking about the general system. Okay, fine.
And so again this brown region is not allowed, and then so when we put out this paper, then there was a small discontinuity here. So we suspected that one can write down another function which would join these two things, and very recently we found another. Oh, sorry, this is so annoying. So we write down, we could able to write down another function which like joins these two regions. So right now we have this picture, and you can see that as delta goes to 1, this value goes to 0.5, and we can actually show that for delta going to 1 from below, this 0.5 value, the lower bound, is optimal. And that comes again, the optimality comes from the looking at the monster example.
But then the upper bound and the lower bound should touch that point.
No, we could not come. So the upper bound will never touch this thing because the C plus is always greater than 1.
Upper bound or the lower bound.
So no.
Basically you cannot push it up, right?
Yeah, so the point is like in principle, like this line could also be down. Like this is not the optimal. So
Okay, there has to be.
yeah. So we tried really hard to make this. Yeah. So we really tried hard to push this down, but like after some point we lost control over numerics. So this is the best we could do.
So what? Please say again. You say when delta goes to 0.
Delta goes to 1.
Sorry, when delta goes to 1. Yes.
And this value of C minus is 0.5, and that is the optimal value. You cannot do better than 0.5 because you can see in Monster, if you take a window from suppose say 1000.5 to 1001.5, there is only one state, and this will give you a factor of half. And because for Monster you have a Rademacher like formula, so we can directly estimate the number of states there, and then this 0.5 saturates that thing. So you cannot do better than 0.5, but you can only do it for delta equals 1. So for like delta approaching 1 from below, but for other values of delta we still do not know what to be the optimal value and things like that.
And is delta equals 1 special because the spacing in the Monster thing of energies is 1?
Yeah, that's what we use basically, like some 0.5 to 1.5 in this window. Yeah. Okay, once we have these results, the best thing to do is to check them. So we check them against various, for example, this is 2D Ising model. So the blue thing, this is a very jagged line. This is like S actual minus S Cardy, where S actual is coming from the partition function. And then our prediction is S minus and S plus, and you can see that these blue lines are always inside the black and the red line. Ideally it should be true asymptotically, but for Ising model it is true even for very less values. And there is oh, so this is for all the operators. Yeah. And also we have seen one curious thing which we haven't figured out why. So for example, when delta is an integer multiple, like delta is an integer, this error, this wiggly thing is much smaller somehow, and these bounds are really off. But I do not exactly know why this happens. This also happens in all the extremal CFT partition functions. Whenever delta equals 1 or integer multiple of 1, the error is like very closely packed around 0. The bounds are still satisfied, that is true, but yeah. So yeah, I do not have very clear idea why this happens. Maybe this has to do with the fact that much of the operators are at spacing of 1.
Right.
Yeah.
Right. In a free theory it's 1. You
Yeah.
expect in an interactive theory it becomes smaller.
Yeah. So
once you go beyond 1,
yeah,
you don't get much.
yeah. So
The delta that you plot, what spin is that?
wait, say that again.
That spin, there's no spin there.
Yeah, there is no
Spin is that?
here in this case.
Yeah.
This is for all spin. Like this analysis is not sensitive for spin.
Integrated somewhere over all.
Yeah, integrated over all spins over that window. Yeah, you can make the analysis sensitive for spin, but yeah, this is not the graph for that. Yeah.
Logarithmic.
Oh, hello.
Yeah. So I just wanted to ask, if you take this left graph,
Yeah.
if you kind of Fourier analyze it, does it look better? Do you know that are there like some, because this looks very noisy, but I mean, what is happening in the left graph? I mean, so you're saying in the one there's very little fluctuations.
Yeah, right, exactly.
But do you know what happens if I Fourier transform the left blue thing?
If I forget what, I cannot catch.
Fourier.
Oh, I see. I'm not really sure.
Okay.
So you are saying taking the actual thing and doing a Fourier transform of the the actual number of states, something like that?
Yeah, or the difference.
Oh, I see. No, I haven't tried that, but yeah, maybe that would reveal something. Yeah, I haven't tried that. Okay, and then you can approximate. Then you can like test it against extremal CFTs. And here again you can see for the low enough values the bound is not satisfied, but this is fine because it's anyway asymptotic bound. But if you go high enough, this thing goes inside the band. And and then comes the optimal lower bound, as I said, for you can see it. So you can prove it analytically using Rademacher, or you can like basically plot it for delta equals 0.9722, and you can see that this oscillation barely touches this red bound. So which means that this red line is optimal, you cannot push it up. and analytically you can show that as delta goes to 1 minus, this has to be 0.5. So that's thing, and then you can also check against the integrated version. And so basically the red line here is the integrated rho delta from 0 to delta, and the black line is the Cardy formula. So you can see that the black line nicely goes through these red jagged lines, and this is a very nice match. And you can also see that, so Bauer and Sasha predicted the error term for this, and you can also check that their prediction of the error term is perfectly fine. Yeah. So, and the way the proof goes, first you estimate for an order 1 window like this, and then basically you take this 0 to delta and break it up in various pieces and estimate it separately, and then you write down a formula for this whole integrated thing. So going from here to there is like another 6 pages of calculation, but yeah. Okay. And then the spectral gap, as I was saying, that basically I can put a lower bound on number of states. I can make the analysis sensitive to primary. So basically I am putting a lower bound on number of primaries in the window of with 2 delta by this thing. Then I find out all such delta i's by choosing different functions so that this thing is positive. If this thing is positive, then if this thing is positive, I know that this window has some amount of states, and then the idea is I have to choose the infimum of all these delta i's, and we will call it delta star. And if we find a delta star, then we know that the spectral gap is bounded above by 2 delta star, because if I have a window of 2 delta star, there has to be some states. So the whole point is, if I make delta to be very small, then I will not find such thing, and then at some point delta crosses that thing. So in this way this can happen, and also it might happen that as I am scanning over various deltas, if I make delta to be very small, then this condition is violated. Then after a threshold value of delta, lambda becomes less than 2 pi, and that threshold value will give you delta star. So this 2 way this bound can work. So there are 2 possibilities. And so basically Bauer and Sasha showed that this is 1.1, and then they conjectured that this has to be 1 because of monster CFT, like you cannot do better than 1. Then we basically wrote down this magic function which satisfies all these nice properties. So as epsilon is greater than, if epsilon is greater than 1, then the Fourier transform satisfies this property, and you can see that this function is negative outside epsilon over 2. So and you can let epsilon going to 1 limit, which takes this lambda going to 2 pi limit. So this function precisely proves that 2 delta star is 1, and the 1 has to be optimal, because suppose you write down something which is below the 1, suppose 0.9, then you can consider the monster CFT example, and you can consider a window of 0.9 so that there is no integer in between, so that would be a violation of your statement. So 1 is the best you can do.
Also free scalars, right?
Yeah, right. And so this is the result, and then for improving the upper and the lower bounds, the C plus and C minus, we used these particular functionals. So, and this function also appears in the sphere packing problem. So during the same time this paper by Hartman, Dalimil and Rasteli came out, so this like while writing down this function I have some influence from this paper. So, and this is the function that is used for proving the sphere packing problem in 1D, which is pretty trivial, but mathematicians do get insight from writing down these functions. So, and all these functions have this property that lambda is less than twice pi, and basically it's above and below the bum indicator function. Okay, good.
So do you have any intuition as to why this appears in the sphere packing problem?
Oh, this one. Oh, sphere packing problem. This one. Yeah, the intuition is that this function has poles at right points. This function has poles at right points, and in the sphere packing problem, when you consider the lattice, then you want the things to be at the proper having poles at the proper points. So that's how it appears in the sphere packing problem. So there is a paper by Henry Cohn and Noah Melkis back in 2004. They try to do it for higher dimension, and then lot of intuition is coming from 1D. So they explain the 1D case, even though it's very trivial in 1D. They explain the 1D case, so it's very nice. So some of the intuition came from that paper also. I was also reading this paper and that paper at that point of time. Yeah. Hello.
Yeah. So this so you're saying this about sphere packing problem, but is it somehow also related to some kind of eigenvalues of random matrices or something that because of some of these functions look like the kind of things that you see in eigenvalue distributions, and I was wondering whether you can make a statement to some extent that the way these things fluctuate.
Yeah.
The stage fluctuates, whether you can relate it to how some kind of a random matrix eigenvalues are spread out. Is there some statement like that should be made?
Yeah, I guess it would be really great to make those kind of statements, but it's not really clear how to make it very precise or say things like people expect in chaotic CFTs the eigenvalues are distributed like random matrix, but then it's not really clear how to do it in a CFT. Like first of all, I guess it's not clear to me like how you make sense of ensemble in a 2D CFT case. Like normally in a random matrix case you consider an ensemble and there is a sense of distribution, but in the 2D CFT case, even if you say the CFTs are chaotic in the normal slogan, like the normal way people say, it's not clear to me how to first create an ensemble and then make statement about the ensemble.
But you can make many energy windows, right?
Yeah, so that oh, I see, you are saying yeah.
To identify the statistics of the spectrum distribution.
Yeah, maybe it's an interesting question. Like it would be really great to figure out those informations from this kind of techniques, but it seems really hard.
I'm going to have to go very soon. I just want to ask a quick question. Suppose you relax the condition that your ANs were positive.
Yeah.
But you added more information. That is that you had the information of this high temperature partition function, not just for real beta but for complex beta.
Oh, so here actually we are using for complex beta. So I just inverted z of beta plus it, remember, and then I am doing the modular transform. So this actually knows about, and that's why it is like complex Tauberian theorems. Like is.
Okay. So then if even if you allow your A's to be negative.
Yeah.
I mean, one of the lessons of this index stuff with n equals for angles is that if you go up under the complex plane,
yeah,
then you recover good information about the high temperature group.
Yeah.
So I was wondering then, by seriously using knowledge of what happens in the complex plane, could you imagine more general sense planes?
I see.
So let me just give you the intuition. The intuition is that if you've got very rapid oscillations,
Yeah.
And that oscillation happens at some length scale,
Yeah.
then you can compensate for that oscillation by turning on an imaginary part for beta.
I see.
That will cancel the fluctuation in phase.
Yeah.
And then you'll be able to count the number of states.
Oh, I see. Yeah, yeah, that seems possible. In fact.
Shifting this window in the Fourier domain, which is centered at 0.
Yeah, it's like it's you are shifting it slightly up in.
Let's talk about thickness in the support plane.
I guess. That's right.
Yeah, that's an interesting idea. So basically you are saying instead on the real line I am slightly moving the real line up on the imaginary line and drawing a line parallel to the axis, and because I am going slightly up on the imaginary plane, then
you're inducing an oscillation which can cancel also.
Yeah.
So you could, by doing it at every complex value, you can reliably count the number of states that oscillate with that frequency.
Yeah, this seems reasonable.
And then sum them up.
Yeah.
And
Yeah.
It already goes to the
Yeah.
Yeah.
If you could do that, I think that would be very interesting because it would tell you how things that.
Yeah,
Yeah.
I see.
But
Yeah.
there is no additional constraint kind of like modular.
No additional constraint, but you know the high temperature. Let's say that in the case of the n equals 4 index, where I give you the analog of the high temperature partition function,
Yeah.
but for all complex values. I want just some surety about what you can say about the number of supersymmetric states from there. At the moment, what people do is they take that and then they invert it,
Yeah.
assuming things are okay.
Yeah. Yeah.
But it might be nice to have some clear statements about that.
So the high temperature answer is what you have in the paper.
High temperature answer for real values of chemical potentials, what we have. Bellini and Kim and so on have been computing what it is at complex values, right?
Oh, I see.
And
And they
then
have explicit formula.
there's only some things known. But let's suppose we had explicit formulas.
Yeah.
What could you say about that?
Yeah, this could be a potential application. Yeah, definitely.
Okay, sir. Thank you.
Yeah, yeah, sure. Okay, so next the natural question is how to generalize this on the asymptotics on the plane. So on the plane I can approach infinity along various curves, and the idea is for various curves you can estimate the heavy part and derive some like formula. So I will just as I say, it becomes a two variable problem, so it's much more complicated but still can be done. So and you will see that the error actually depends on how we approach the infinity. So we can, so roughly here the idea is basically you consider a line like this, and so the vertex of the rectangles lie on these lines, and then you take this upper vertex and let it go to infinity along this line and estimate the number of states in this box.
Sorry, just one second.
Yeah.
So in this one-dimensional analysis, you had this the main statement somehow seems to me is that lambda must be less than 2 pi. Okay. So
Oh,
that's
yeah.
how you determine using modular invariance the kind of support that it
Yeah.
should have
Yeah.
in the frequency domain.
Yeah.
Now there is a similar statement.
Yeah.
First,
Yeah.
And that's like a 2 pi circle or something like that.
Yeah, so that's like a, so it's not really twice pi, it actually depends on the how you are approaching the infinity. And in fact the bound we found is, so the bound that is in this paper is not really optimal. Then Bauer and I came up with the optimal bound only for the diagonal line. For still the off diagonal approach we still do not know.
No, but so I was thinking, you can break up this optimal bound question into 2 parts.
Yeah.
First, figuring out this kind of.
Oh yeah, so this becomes okay. Oh, I see. So
that is some fixed thing.
Yeah.
Which you will just be
yeah,
able to fix, right?
yeah, right.
Then once you have that, what kind of functions?
Yeah,
you
yeah,
write down
right,
that property
right.
Which will minimize and maximize.
Yeah, exactly.
So
Yeah,
the first part.
yeah.
Is what?
Is a square?
Circle or something.
Not circle. It's a square.
Square.
Yeah.
Okay. And then this analysis is about how what sort of
Yeah, functions,
you
yeah,
can write
yeah.
down into dimensions so that it has support over 2 pi square.
Yeah. So as I was saying that this it's not really twice pi, it actually the approach gamma, so there is a factor of gamma which relates how it approaches the infinity, that also appears here.
Can you not scale H and H with different powers, let's say, something like let's say spin and dimensions are scaling with different powers. So let's say spin is
Yeah, that's what I did here,
That's
like
what-
H, there are various curves. So this means this is H bar and this is H, and for this line H bar is H to the power 1.9, and this is H equals H bar, and this is other one. Is this what you are talking
yes,
about?
Yes, it will be something like that. Yes.
Yeah.
And then is in anything nice happens at any interesting fractional power, like in terms of delta and J, this dimension and spin. Is there any particular scaling for which you get something very interesting, some bound becomes optimal or something? Is there?
Yeah, that's what I was saying, that in Bauer and I was able to figure out that at least along this line we have the optimal bound. For other lines we have some bounds, but probably those are not optimal.
This line is the H equal to H bar.
Yeah.
Why do you expect something like that?
Why do I expect? Because in higher dimension, then the delta and the j are scales in differently. Let's say delta is like, j is like delta to the d by d plus 1. So that would be a special line in higher dimensions. And if you have other symmetries, you might have different lines. For example, BPS states will be delta is equal to j. So I was expecting there might be some very interesting behaviors depending on that.
Let's see. Yeah, here.
But there's some charge statement. This is still.
Yeah.
Right, rotation.
About charge.
Rotation.
Okay, so basically we wrote down this formula, and there is a error term which actually depends on this gamma factor, and gamma is basically the ratio of h and h bar as you approach infinity. And again you can check against the favorite 2D Ising model. So I guess here you cannot really see. So the black line is the Cardy formula, and there is a bunch of jagged red line which almost crawls along the line. And then you can check the error times the inverse of this polynomial is bounded within a band. So this shows that this error is optimal. You cannot do better than that. And also you can do an order 1 analysis. So basically instead of interval, you consider a square or a circle on the h bar plane and estimate the number of states within that thing. And in the same way you can put some bound on the order 1 correction, and again you can show that this is bounded below and above by red and the black line. And we haven't tried anything to optimize this black and the red line, so that's another question, like what would be the optimal case. But again, so the point is the functions we wrote down for the 1D case would not work here, so you have to completely find some other functions. So, and then you can also do this kind of things which gives you some sense of distribution of operators in the plane. So you can estimate the number of operators in this blue rectangle divided by the number of operators in the red rectangle and see that these are exponentially suppressed. In the same way you can estimate the number of operators in the red square divided by the number of operators in this big triangle, which is like polynomially suppressed. So basically you can dissect the whole plane like in the rectangles and in the how do I say, right angle triangles, and estimate the number of operators lying within. So you can do this kind of analysis. And also, as I was saying, you can probe the asymptotic gap in terms of circles. So the idea is you are considering circles on the plane and then let the center of the circle go to infinity along various lines, and ask yourself what will be the minimal radius of the circle so that it contains some state. So in this paper we are able to show that this is 1.56 times gamma, where gamma is this approach, and they, yeah.
Sorry, this spin is a discrete quantity.
Yeah. So
if you increase it a little bit, you are bound to encounter something which would just have a higher spin. Oh no, you are saying that would be far away in the delta space.
yeah, right. So we could prove that this is 1.56 gamma, this upper bound, and we believe that this could be reduced, and at least for h equals h bar we can show this is 1 over square root 2, and this is precisely the one where you have a chiral monster and an antichiral monster, and all these integer points are spaced. So the optimal circle is this one with a 1 over square root. So this is kind of very nice, but the point is we could only do it for h equals h bar line. For other lines still we haven't done anything like. So I guess for the h bar case the problem is following. So either you could do something better on choosing the functions, or you could do better something here. So it's not very clear exactly where you have to do better.
But that's something that's fixed by modular, right? So why is there this?
Oh, so the point is, so the point is like when you are doing the h case for the heavy state, you have to cut the plane in various ways. So maybe a better cut would give you a more nicer bound. It's not a priori clear, but on this delta plane, on this delta line, it was very clear, like c over 12 c less than, that's the only way to do it. But on h bar, it's like you have various choices.
In fact, if you have a CFT with U1 symmetry,
Yeah.
then for the partition function which has a chemical potential
Yeah.
with the U1 symmetry,
Yeah.
I suspect that the line which should be nicest
Yeah.
it would be not case for which you have get nicest results, probably not this line, could be some other line. I'm saying this because here the global symmetry is rotation,
Yeah, right.
basically rotation, H and H bar. So, and in high energy sector, rotation is like energy. So this is the line which you are getting in the high energy sector. If you are looking at black holes,
Yeah.
then energy is like rotation
Okay.
for the rotating black holes.
Yeah.
So therefore, I would imagine that if you have a different global symmetry, some you want
Yeah.
global symmetry, which
Yeah.
is not space-time symmetry.
Yeah.
For that, probably the most natural line would not be this. Probably the most natural line would be, spin is like dimension to the power half, like square root of dimension probably. This is the natural line.
Yeah. So the point is, if you assume something else, then the analysis would change, and
Right,
yeah,
just-
yeah, yeah,
just as a
yeah,
comment.
yeah, yeah.
Probably
It
that-
might change. Yeah, yeah,
It's just from the large charge analogy I am saying that.
yeah, yeah. It might change. Yeah, I completely like I cannot really see it changing or something, but it is quite possible. Like I would believe you, if change.
Pseudo atom section.
Yeah.
Yeah.
And there, if you have even symmetry,
Yeah.
then the delta goes like this way.
Yeah, yeah,
Right,
yeah.
so that would be natural,
Yeah, but here it is not delta equals to this is L equals 0.
Right.
And then we came up with also a nice inequality which tells me that the twist gap times the area of the minimals, like the area of the minimal circle which has some state, has to be bounded by this number where r is 2.21. Again, we believe that this could be improved, and this inequality
This is centered around which state? Your origin?
no. So this is like so this is the area of the circle. So how would I say it? So this is the area of the circle centered around any point. So this is the area of the circle with the radius being equal to the minimal Euclidean distance between different operators. So you consider circles along the plane, consider all the circles, and consider the minimum, like the minimum of them. Like it's a generalization of minimal gap in a 2D case.
So if I have a CFT, I have many operators,
Yeah.
and then if I plot all of their H and H bar,
Yeah.
and I choose the smallest area.
Yeah, smallest distance, and consider the circle with the diameter as the distance. Yeah,
So that would be G.
that would be A, and times G is the twist gap.
G is the twist gap, and this is bounded by
This number.
R is a numerical factor.
Yeah, R is a numerical factor, and this comes from the fact that if you assume a twist gap, then this bound on lambda is related to this G, and because lambda is related to the gap, so this gives an inequality like this. And
Isn't it more natural to work in projective? So you consider H and H bar in terms of radial coordinates in the H bar plane, and you take radius to infinity and probe as a function of theta.
I see. Yeah.
So that you go to infinity once and for all.
Oh, I see. Maybe. Yeah, I guess for us it was most natural to consider H and H bar because it's like e power minus beta H and minus beta bar H bar. But yeah, I can see like you are, yeah, maybe it's possible. And then you can also do all this analysis for large central charge where delta scales as C, and you can actually show the sparseness condition comes out naturally in this condition. You can also show that the Cardy formula exists only when epsilon is greater than 1/12, and this was also in HK's paper because they showed that the Cardy formula only exists if the delta is greater than C/6. So this is precisely this point here. And again, this analysis can be generalized for where H and H bar both is of the order of C. And again, you can prove some bounds on this thing, but the point is here our result differs from the HK's result. So HK's result in some sense is stronger than us, but we suspect that's just because we are trying to be very rigorous, so we are losing some power in that sense. So, or maybe our analysis can be like done in a better way, so reach the HK's, what HK's claims for in this case. But for delta case, like the HKS matches with the Tauberian analysis completely. and these are meaningful for holographic context because it's a large CFT with a sparse low lying spectrum. And then currently we are also working on this Cardy formula. So, this is like a fixed spin but large delta, and again we can write down a Cardy formula for this fixed spin large dimension and prove some bounds on the say. So, basically you consider some interval on these lines and estimate the number of states, and you can ask like what would be the minimal interval for this happens, and again the minimal interval becomes like 2, which is again saturated by monster, because if I go up by 2 unit then the spin remains same, h goes by 1, h bar goes by 1. So, again we can show optimality and all this thing goes through. And one of the crucial input is this calculation is spin is an integer, because if spin is an integer then I can take my partition function and do a Fourier transform, and that Fourier transform is like from integral is from minus pi to plus pi, because if it is an integer, and because it is a finite interval integral. So, we have the control and we can go through all the things. So, this is work done with Bauer very recently, and so this concludes the state of all the density of states. And now, so if you guys have time I can go through OP coefficient briefly, or up to you guys. Okay. I guess I need another 10-15 minutes. That's it.
The only thing is lunch. So maybe you can.
I can briefly tell you. Yeah. So roughly the idea of OP coefficient is same. Instead of density of states, here you get something which is weighted by the OP coefficients, and the idea is you want to estimate the asymptotic growth of the OP coefficients. So, instead of density, but here the problem is that the OP coefficients can become negative, and so naively you cannot go through this whole procedure. But then when you look back into the Tauberian literature, it actually allows for the coefficient to be little bit negative as long as you are not screwing up the asymptotic behavior. So, the whole point is you can, so suppose you prove a theorem for a positive coefficients and then you add up some quantity to that which is a little, so it's something like this. So, suppose you prove suppose you have a quantity like this, e to the power minus 1 or something like this. So, I can consider a new quantity which is, sorry I was writing b of e like this, and then this becomes a positive quantity, and then I can implement all the analysis for this b of e, and once I have the asymptotics of b of e, I know the asymptotics of a of e. So, I know the asymptotics of e inverse because this is a function I cooked up. So, as long as this E inverse does not spoil the asymptotic growth like the behavior, I can still deduce the behavior of AE. So, roughly this is what we have implemented in this context, and then basically this is also like, so initially I proved a lower bound and then Bauer pointed me out that we can also prove an upper bound.
So you need to know, here you need to know something about how negative it could be at most.
Yeah, that is what I said here. So, A of E is bounded by E inverse.
But for OP coefficients, what is the intuition? I am not even getting. For when you have OP coefficient, they could be as negative as you like.
Oh yeah. So the point is, that's what I said, that at least only for this restrictive case we can put a Tauberian theorem. But if the OP coefficients vary widely and doesn't satisfy this theorem, then we cannot do anything rigorously. Yeah, so these proofs are only assuming, so it's not really E inverse in this context, but it's something like, so it's an exponential function of square root E.
Right. But in higher genus bootstrap, I
Yeah.
think one can set up a situation how you get a square of this.
Yeah, of course. If a genus 2 partition function, right, this it will be C H H H square, and then you can do this. Yeah.
So there you can do
Yeah.
more.
Yeah, there you can do the normal thing. Yeah, exactly. Yeah. For genus 2 you can do the, in fact for not only genus 2, in any case where you have this square thingy like positivity is guaranteed, you can do the normal thing. So, and also here another interesting thing happens depending on whether the so if you take the 1 point function and do an Q expansion, then the first state that contributes is a non-trivial state where f chi o chi is 0. So, this chi is not identity because the 1 point function of primary is 0. So, depending on the value of delta chi, you have different kind of growths. For delta chi less than c over 12, you can show an exponential growth, and when delta chi is greater than c over 12, you can show that this has a polynomial growth.
Chi is the lowest operator which couples with O.
Yep. And then basically we have some graphs, we check with 2D Ising model, we can show that it's like almost saturated, and I guess something is going on here.
Will you be done soon, or yes, you have to? Yeah, we have reserved the room for discussion. At 1:30? 1:30. We'll 1 to actually reserve it from 1 to 2:30. We'll close it.
1 to 2:30.
Okay, I guess I will be done soon. So for so the point is for delta chi less than c over 12, we have exponential growth, and for greater than c over 12, we have a polynomial growth. And again, you can check it for 2D Ising model. If you take this operator, like these are 4 copies of Ising model. With this thing, I have to take 4 copies because I want to make delta chi less than c over 12, and then you can check is satisfied the bound. And if you just check for the normal Ising model with delta chi greater than c over 12, and then you can see that this is polynomially bounded. So, I take the Q expansion of eta to the power 4 and do this and see this is satisfied. And for all these cases, the extra condition I put in is satisfied. So, and then one can try to think of more stuff, like with Diptarko I have been working on these other OP coefficients. For example, for HLL the positivity is guaranteed, for HLH prime also positivity is guaranteed, for this thing also positivity is guaranteed. So, this is kind of easier than this thing. So, the only way is like the only tricky part is you have to invent some HKS techniques for this thing to estimate the heavy parts. And then another question is whether there is relationship with the Rademacher formula. So, recently Alde and another person wrote a paper on Rademacher formula, so that might be useful in this context. And as I said, the Tauberian techniques are useful in context of asymptotic analysis. So, it is not only related to 2D CFT. So, it should have a wider applicability. Thank you.